Good morning. This is the second instance of the lightning talks. We are ready to go. The first speaker will be Ilf, and he will be talking about Schleuder, which can be used to encrypt email mailing lists.
Almost full screen. It is F11. I think it'll work like this. All right. Glad to see so many showed up, even though it's so nice and sunny outside. So let's do a quick round of hands for a little interaction. You're not all just sitting here. So who of you encrypts emails? That's almost everyone. And who of you uses email lists? That's also pretty much everyone. I don't know. They don't use email or encrypt email lists. And who of you actually uses encrypted email lists? 1.5. Okay, that's a problem. We need to fix that. Why is that not the case? Because it's cumbersome and there's very little software to do that. Actually, the problem has been around for quite a long time, and there are a dozen hacks and scripts of people who have previously tried to implement email encryption on mailing lists. I have like a little inventory of neat little script which some people wrote to scratch their own itch, but the problem with most of them is they're archaic, unmaintained, old, and there's very few running code. Now there's one tool which I want to advocate for here. It's called Schleuder, and it is actually running code and in active use to encrypt email lists. So Schleuder takes the approach of being, we call it a friendly machine in the middle. So you get an encryption key for a list, you encrypt to the list server, and the list server decrypts it. It does have the clear text, but then re-encrypts it to all individual subscribers. Now there are multiple approaches to fix the problem of the list server not having access to the clear text, but they involve way more complicated things, and there's no good running code. People don't use it. So we like this thing called the friendly machine in the middle, a mail server we trust, set up and run our own, still fixes a lot of problems of unencrypted emails, even if not all of them. And Schleuder just works. We have a couple of hundred lists, we have thousands of subscribers, and we have enough lists with hundreds of people on them. Key management can be a little of a hassle. If you check it out, come talk to me. But in general, it just works. Now, Schleuder is not a full-fledged mailing list manager like Mailman or some others. It doesn't have archives, it doesn't have digests or any of those of that fancy stuff, but it does re-encrypt and send emails to subscriber, and it does have a nice bonus feature, what we call resend. It can be used for internal group communication, and then can also be used to mail to other people from the Schleuder instant to non-subscribers. So you use it as your internal little collective email to debate, and then you can also send it and say X resend and send to an external person, also encrypted or not encrypted, depending on your settings. So basically, Schleuder has been also a Scratch My Own Itch project. It's been in various stages. The first was just a Perl script written some 22 years ago, but it went through multiple iterations, now up at version 3. It does use email encryption with OpenPGP, with the pretty widespread GNU-PG implementation. Unfortunately, that seems to be still the major one for OpenPGP out there. It doesn't use GNU-PG directly. None of you should do that. It uses GPG-Me, which is a pretty nice library from the GNU project for automated interaction. Schleuder itself is written in Ruby. It does use this Ruby gem called MailGPG. It's relatively straightforward to install on a recent Debian machine. It's in backports, so apt install from backports and you're done. Try it out, run it, and if you want, we're also still developing this add-on called Schleudr Web because most of the interactions with this tool are currently done by email commands. And we know people like to use web for things just in order to scale it. At some point, you want to have users which, feel more comfortable in a browser checking boxes. That's pretty much it. It's a lightning talk. It's pretty quick and dirty. But please check out the project at schleudr.org. If you have any questions about it, feel free to approach me or contact the team at email or IRC. We'd love to hear feedback. We love to see it in more widespread use because clear text email has to die. Thank you very much.
Yeah, hello everyone. I'm here to give a status update of something called Data Co-op. Remember the name, data.coop. That's also the website address. And I'm sorry that Kramse isn't in the audience. I would have liked to have surprised him today that Data Co-op exists and it's doing some stuff. So let me start by introducing what Data Co-op is. We're a society in Copenhagen, or a cooperative, who wants to run our own infrastructure to store the data belonging to the members of the cooperative. And we have some ideals for that. We want to protect our privacy, and we want to encrypt stuff so that when we talk to other services on the internet that we provide the right encrypted mechanisms. And we want to use decentralized services, so we want to, say, be one of the instances of a decentralized world. What we also aim for is zero knowledge, so that Data Co-op in itself does not have insight to the data of its members. And that's an objective. All of this we do so that other people can also use it. We're in Copenhagen, and we want to be a member base who kind of live and meet up in Copenhagen, so that so you can say there's also a goal that everyone in Data Co-op should be able to meet each other, so that you kind of know who's also your fellow data consumer or hoster. Yeah. So, as I said, this is a status update. Since this all got started from an idea, and a bunch of people went and constituted this society, we have registered the society, and we've created a bank account. So that can also be a challenge in Denmark. But we are past that, and we have a Git server running where we are developing our solutions, and sort of we're in the prototype phases now of some of the first services that we want to run together. So this is, for instance, a Nextcloud server. We have also purchased 2 Rex servers, refurbished, that cooperative owns. And they're going to be put into production this year. That's why we need more members, because if more members join in, then we can pay the costs of running these servers together. So we have a bank account, and it's pretty easy. I didn't put the price on this slide for the annual membership fee, but it's 300 kroner. And we are looking for a model where we contribute by annual fees, but also that you can scale sort of what you are consuming of services on the common platform and pay for that as well. And up until now, it is just as simple as writing your name on the bank transfer and sending an email to me. And how much time? Okay. I will end here, but remember the name data.coop. Please visit the website also, where you can read our constitution and sort of see the principle that this is founded on. And we have meetings and so on in Copenhagen, where you are welcome to come by. We kind of hang out here in BornHack. There are 4 members of Data Coop here, and we also often hang out in Cryptohagen.
Yeah, so I'm going to talk about something I developed in the kernel called Express Data Path. I'm a principal kernel engineer at Red Hat. That's the Red Hat sort of dead giveaway. So what is this XDP, right? I obviously assume everybody knows what this is because I sort of developed it and put it in the kernel. It's been in the kernel since 2016. But I guess not all people know it, but it's actually kind of sort of revolutionary what we did. So it's basically a new layer in the network stack. Before we allocate our metadata structure called the SKB in the kernel. And it works on the driver level hook. So just we now have a hook in most of the drivers, the high-speed drivers at least, just after the DMA gets synced to the CPU. This means that we are extremely fast. We're competing in the same speeds as if you know what DPDK is, or NetMap, which FreeBSD has, which also works on the same layer and are reporting these amazing performance numbers. Now the Linux kernel could do the same thing. And I'll talk more about what kind of actions and decisions you can do. And one of the reasons we are so fast is also we avoid any memory allocations, and we do recycle schemes and all kind of stuff. Like the solution called DPDK is completely kernel bypass, also NetMap. But my solution, or this XDP solution, is not bypass. It actually still keeps the package inside the kernel, and the kernel is the data plane, and user space is then the control plane. I'll explain that. So the important point is that you actually get programmability, and that's what I want to talk about here. I want you to actually use this and give you some hints to it. And let's see. So what you actually get is fast and programmable networking at a very, very early stage. And this is actually giving superpowers to all of you, because you can now load these programmable program snippets directly in the network hardware drivers. It's a software solution, so if a driver is missing it, you just add it. It's only software, and you can still operate at these amazing speeds. So you're in control. You upload a BPF program, and what you get is you get really, really early access. You can both read and modify, and that's actually very, very strong. So what you can imagine is that, because this is just a dynamic program you're loading, you can imagine that the Linux kernel you have running, you don't want to reboot that. There's a new protocol coming. Shit, what should I do? Should I have to reboot the kernel and add support for the kernels for this new protocol? Well, you actually don't. If it's just an encapsulation, you can just program your own decapsulation, modify the packet, and send it onto the normal network stack, which will then, you can map it into whatever you want. You can just add a VLAN header or do something else, and then you can map it in. So it's actually quite powerful that you can modify the packet at this early stage. It's almost like you modify it on the wire before the Linux kernel actually sees the packet. That's a very powerful feature. You can take actions really early, which makes it quite perfect to implement denial of service protection. So if your machine is under the denial of service, so it used to be that the fastest hook was the IP table's raw table. You could install filter rules there to protect your server. But now we actually have another hook that can run wire speed on one CPU. So if you get under DDoS attack, this would be my tool of choice to protect my machine. And I have some links to some examples you can actually just download from GitHub and run. And Facebook also uses it as a load balancer. But really, you can figure out stuff to do yourself. So the limit is your imagination, and the limitation of what the BPF hooks can do, because there's some limitations associated with that. Because I think I'll talk about it next slide. We actually allow you to load user bytecode into the kernel and execute it for you. But we put some restrictions on that to make sure this is still safe. So yeah, this is about the split between the data plane and the control plane. So the data plane is still inside the kernel, and it's split into the core kernel, the fabric that is in charge of moving these packets really fast. That's my job. And then we have the BPF program in the kernel, which can take logical decisions and actions, and read or write access to the packet. What?
You're running out of time.
Yeah, sure. But that's not that many talks on the program, right? I only had a few slides left. So it's not my role to write this program. It's my role to make sure that it's safe to execute it in the kernel, but I'm allowing you to load this program. But the control plane, the way I see it is that you from user space load this program. You can control the programs by these maps, and that's how you control the whole thing. Everything goes through a system call. The actions you have available is drop, pass, TX out. That's what Facebook community use. We also have an abort and a redirect, which is very interesting. I don't have time to talk about that. But it's really about cooperating with the network stack. We can push and pop headers and change which functions inside the kernel will get this. These are the sort of the features you get. You can also propagate information from this stage into the SKB. There's 32 bytes you can use for transferring metadata you obtain in this stage to the next SKB stage. It's a fairly advanced feature, but I've not seen that many people use it, but it's available. Let's see. Yeah, this is about the XDB thing, is that this is a sandbox. So you run code inside the kernel. You have to be root to load the code, but still we must make sure that you cannot crash the kernel. And you can, XDP is one user of this BPF stuff. You can also use a trace point and other stuff. But in each hook point, you have some possible actions and access to some helpers. Yeah, I'll just get to this. This is sort of my final slide. So if you want to get started with this, what I recommend is you do, instead of writing this BPF bytecode by hand, that you actually use the CLang compiler. You write your program in C. I call it restricted C because this BPF have some limitation of how many instructions and loops and stuff. which don't allow you to load unsafe programs. But still, you write it in C and you compile it, and I recommend looking at the kernel repository. There's a samples BPF directory, and I have my own GitHub repository where you can go into that and you can basically run make and see different examples and try to load them, and you should work out of the box. So I hope people will actually use this kind of stuff. So that's it.
Awesome slides. So I'll be talking about an SSH agent for cubes. So an SSH agent is a program that you use for storing your private key. And the idea is you, for example, don't want to enter your password all the time, and also to keep the private key separate from the SSH program. And Cubes OS is based on Zen, and you run applications in different VMs, and you can use this to keep your web browser separate from your mail client, and have a VM for secret keys. And it has an extensible RPC mechanism for communicating between the different VMs. And this is awesome. And someone has made a project called Split SSH Agent, where you run an SSH agent in cubes within a separate VM. So in that way, whatever VM you run your SSH client, it will not have access to your keys in any way, like not even the encrypted files. So that's great, but there's one downside to this, and it's that you have to run a Linux VM, and this involves some hundreds of megabytes of memory just for running this SSH agent VM. So my solution to this is to write a new operating system using Mirage OS, and it's a library operating system, and you write single-purpose operating systems, and it's in type-safe OCaml. And when you write a Mirage OS VM or kernel, it will only contain the code relevant for your task. So for example, in the case of an SSH agent, you will not have a TCP IP stack and so on. So maybe you can even click. Yeah, I implemented the SSH agent in Mirage OS, and it's fairly bare bones. It only supports RSA keys. This is mostly because that's the only encryption support that I could find currently. And the SSH agent runs in 16 to 20 megabytes of memory, the whole operating system. And yeah, it used to be 16 megabytes of memory, but I think some dependencies grow a bit, so you need a bit more memory. And it's fairly simple. The agent logic is about 58 lines of code, so you can read it and modify it how you like. And another 66 lines contains some cubes and RPC logic. Yeah. So I'll just end it here. If you want to give it a try or want some help with it, say hello to me and we can take a look at it. It's a bit involved to build, but we'll manage, hopefully, and maybe improve. Thank you.
But I noticed this paper was published a few days ago, or at least I got it in my RSS reader, and it's the paper will be presented in a week. Yeah, next week, it's like the 27th of this month they'll present it. But the paper is about the growth of complexity in the Linux kernel, and they take a look at between 100 and 200 vulnerabilities in the Linux kernel, and the conclusion is that 96% of them would be prevented if instead you had an operating system with a formally verified microkernel. And they say that without the formally verified microkernel, the simple microkernel, you get 30% reduction. And the paper mentions Google Fuchsia, which is Google's new microkernel operating system, and so I don't think that's necessarily a coincidence, and so I think we'll see more of these sorts of papers. But the paper is a bit flawed that it assumes that you have a microkernel-based operating system with all the capabilities of Linux, which doesn't exist. But there are there are some modern microkernel operating systems, and actually I run one. So these slides are, yeah, on my laptop I'm running a L4 hypervisor, Nova, and so it uses like a declarative model for defining the system, and so to illustrate this current scenario with the slides, I have some routing information at the top. I have this static system that provides a timer, provides logging, a CPU, of course. I have a window manager. I have a component for modifying the root path of this slide program, this PDF viewer. And the PDF viewer doesn't have any logic for loading files. It just loads the first PDF it sees. So I have to use a to root here. And this is quite simplistic, but yes, and so the operating system is Gnode. The base framework is Gnode, but we refer to this as Sculpt with the graphical UI because there's no, the operating system doesn't imply that you have a network or a frame buffer or anything like that. But this year we've released the Sculpt Live image with this file system switcher. And so I can drop the slide configuration, and then I can drop in the configuration I normally use. And I can show you a few things we have working so far. Unfortunately, I'm having network problems right now. But let's see. Yeah, so we don't have UI for starting and stopping programs, so we have these XML files. So this is a file for launching packages. So yeah, we have Qt ported. Yeah, you can use the Qt libraries, and there's some POSIX support, but we don't have the sort of full range of facilities you'd see in Linux. And but we also have hardware-assisted virtualization. So I have a NixOS VM loaded here, and I can start another one. I turned off the network bridge. Oh, all right, my time is up. All right, well, you can see the VMs are booting. Yeah, if you have questions, I'll be around. And I have USB sticks if you want to try it on your machine. We don't support all hardware. We don't support AMD processors, but ThinkPads are generally you'll be okay. Yeah, thanks.